Hello, Honors Chemistry, and welcome to the back part of Chapter 3,
where we're going to talk about 311 and 312, where we very specifically talk about how we relate specific heat, temperature change, mass, and heat. So we talked previously, right, about how temperature and heat, not the same thing, right? Temperature has to do with the relative kinetic energy of the molecules that we are taking the temperature of, right? Higher temperatures correspond to higher kinetic energy, meaning the particles are moving faster. Lower temperatures correspond to lower kinetic energy, particles are moving more slowly, right? Which then goes hand in hand with the fact that, in order to freeze something, we typically need low temperatures, right? Or lower anyway, right? Because we have to slow them down enough that they will settle in, sit down next to each other, and let those attractions between the molecules form, right? So that they stay still, right? Likewise, high temperature, if we think about what that means, the particles have to have enough energy so that way they don't sit next to each other, so they don't get trapped by the forces of attraction that exist between my molecules, right? So anyway, temperature is about the movement of my particles. Heat is about how much energy is transferred when something at higher temperature comes into contact with something at a lower temperature, okay? So, obviously there must be some way to quantify that, right? And again, a thermometer is only going to give you a picture of the kinetic energy, not the heat exchanged, right? Where heat is a measure of joules or some kind of joules, like megajoules or millijoules, depending on what size exchange we're talking about. But heat is always going to be in joules, right? Not only joules, but we also have to think about signs, right? If it's a negative value, then what does that imply? Right. Then that means it is an exo process. If it's a positive sign, that means it is an endo process, right? Meaning whatever process that substance underwent, it required the absorption of energy to get it done, okay? Mass is measured in grams of whatever substance it is that we're talking about. C is our specific heat capacity, which is joules per gram degree Celsius, right? And so even though there are multiple parts, it works just like every other unit that we talked about previously. And for those of you that figured out that bonus on the test, right, really it's the same thing as any other conversion factor, right, where 1 joule is equal to 1 gram times 1 degree Celsius, right? So we could use this however we want. We have this equation, which allows us to just move variables around, which is something that seems very familiar, right, from math class. Likewise, we could just always think about this, and we would just always set up whatever math we were going to do in light of what units we need to cancel and what units we want to solve for, okay? Things that have a higher specific heat, right, so water, for example, with its specific heat of 4.184 joules per grams degree Celsius, right, has a relatively high specific heat, whereas most metals sit in the somewhere of less than 1 joule per grams degree Celsius, right? Now, what that means is that water requires more energy per gram to go up by 1 degree Celsius, yes? Water requires more energy per gram to go up 1 degree Celsius than most metals do, right? Which goes back to that observation, right, from your guys' book, right, about how the pan heats up significantly faster than the actual water does, right? Things that I assume we've already observed, right, and just never really thought about the relationship between, okay? Then that brings us to temperature change, right? Temperature change is how many degrees it goes up or down, right? Now, a couple of things to note here, right? Delta T is always T final minus T initial, right? And every time we talk about delta anything, it means it means the final scenario minus the initial scenario, right? And that's what delta T equals. So depending on what the question asks of you, right, you might solve for delta T as an intermediate step and then subsequently solve for T final or T initial as needed, right? Now, the thing to note here is this temperature, if we think about our units, right, this C value is in joules, which means this is in joules, right? Grams, this must be in grams, right? And this is degrees Celsius, which means that my T final must also, my delta T must also be in degrees Celsius, right? Now, since it's a delta, right, meaning one temperature minus another temperature, what would also be appropriate and acceptable? Right, degrees Kelvin, also appropriate because the size of a Kelvin is equal to the size of a Celsius, which means whether I calculate delta T in Kelvin or Celsius, it's the same thing, yes? Whereas Fahrenheit, that's not true and not the same, right? But anyway, things to think about, right, is you can't convert a delta. If you are in the wrong temperature unit, you need to convert your T final and T initial. Yes? Can't emphasize that enough. All right. Let's go ahead and do a few practice problems together because,
Splits where lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium. Platinum, gold to make you rich till you grow old. Mercury to tell you when it's really cold. Thallium, and lead, the bismuth for your tummy. Polonium, astatine would not be yummy. Radon, francium will last a little time. Radium, then actinize at 89. This is the periodic table. Noble gas is stable. Halogens and alkali react aggressively. Each period will see new outer shells with electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, and olevium, nobelium, lawrencium, rutherfordium, wm, sprigium, borium, hesium, meitnerium, dubsinium, rocenium, copernicium, anatrium, flerovium, anapentium, livermorium.
okay. Thank you for listening. Be good. See me soon if any of this is fuzzy. Have a great day. Bye.